Hi, and welcome again to my Physics Online video lecture supplement series. Today's video, we begin the lecture set on electromagnetic waves. So previously in the course of these lectures, we have investigated mechanical waves. These are waves that are basically caused by a mechanical disturbance. They can be transverse or longitudinal, means that either the medium for which the disturbance is propagating might be displaced perpendicularly in the case of a transverse or parallel to the direction in which the wave travels. And we looked at several examples like waves in the water, sound waves, waves on a string, etc. And the main thing with these is that they require some medium which can be disturbed. That means that in the vacuum of space, where there's no mechanical medium, there are no mechanical waves. That means, for example, that you cannot hear any sound in the vacuum of space. You can't hear any sound in any vacuum, simply because there's no medium for the sound waves to travel through. So we're going today, and in this lecture set, to look at a different kind of wave, which is called the electromagnetic waves. And these were first successfully described and predicted by James Clerk Maxwell, and then they were observed within a couple decades by Heinrich Hertz. So we're going to begin by considering what are called Maxwell's equations. And among other things, we will look at some of the previous laws that we've had in the course of these lectures. Gauss's law, for example, and Ampere's law, in particular Faraday's law as well. And Maxwell's equation basically takes Gauss's law as applied to both electric fields and to magnetic fields, and then it takes Faraday's law and it takes Ampere's law, which Maxwell actually modified a bit, and collectively this set of four laws basically predict electromagnetic waves, but they also, along with the Lorentz force, govern pretty much any classical E&M phenomenon. In other words, anything that is in classical electromagnetism, it's going to be governed by Maxwell's equations and the Lorentz law. So let's unpack that a bit, shall we? We'll begin with Ampere's law. So Ampere's law basically says that if you have a current passing through any closed surface, then the magnetic field along the path that is encloses that surface, bounds that enclosing surface, I should say, basically is going to be related to the current passing through the surface by this equation. Integral B dot dl equals mu naught I enclosed. So this is Ampere's law. You know it. Hopefully you love it. This works for any arbitrary closed path. So here's your arbitrary closed path. What we didn't state explicitly when I previously unpacked this equation was that it works also for any surface which is bounded by this closed path. So we've basically treated it so far as if the surface in question is a flat surface like this, but it could in fact be some curved surface like this. In fact, if you look at this diagram, there's surface 1 is the circle, surface 2 is whatever you'd call this shape, the ellipsoid half, or the hemisellipsoid, whatever you want to call it. And the total current which passes through the circle and the total current which passes through this curved hemisellipsoid whatever surface should be the same. Now, so long as we're considering along a single wire, like so, or even a collection of wires, that will in fact be true. So this wire carries current I here, therefore it carries current I here. That means that current I passes through this surface. It means that current I passes through this surface. So far Ampere's law is satisfied. But you can have a situation in which Ampere's law suddenly is not satisfied in this form, namely a pair of parallel plates. So this is a capacitor basically. You got a wire connected here, you got a wire connected here. If you place your hemiellipsoid surface on your circular surface like this, then a problem basically occurs. Namely, as you're charging the capacitor, or for that matter discharging the capacitor, you'll have some current in the wire. That means that you have a non-zero current passing through the circle. But if you look at the hemiellipsoid, basically the one plate of the capacitor is entirely closed up within this surface 2. The other plate is entirely outside of surface 2. That means that surface 2 at no point has current passing through it, because there's no current between the two plates of the capacitor. So that means that you have a non-zero current here and you have zero current here, and according to Ampere's law, B dot dl should be mu naught I enclosed, and that should work for any surface that's bounded by this arbitrary closed path. Well, we have a contradiction now, because you can't have a same thing be at the same time both equal to 0 and not equal to 0. Basically, this current I that's labeled in this diagram is what we might call a conduction current, and it involves the motion of actual charge carriers such as electrons or electron holes that are being actually conducted along this, well, conducting wire. So we'll sometimes refer to that as conduction current, and that is what we have meant so far in the course of these lectures when we say current. So anytime that I've said current so far, it has meant conduction current. And what the point of my suggesting that is that I'm going to introduce here a new type of current that we can use to explain, or really to make Ampere's law work even in a capacitor. And so what happens here is we turn to Maxwell. And what Maxwell said is that for a parallel plate capacitor, the charge that's stored on each plate is given by the capacitance times the voltage drop between the two plates. And this capacitance is basically given by epsilon naught times A over D. That's the permittivity of free space times the area of the plate divided by the distance separating the two plates. And you can multiply that by kappa if there's some dielectric in it, but we're going to use vacuum for now. And the voltage drop in turn is the electric field, which has a constant magnitude, times the distance between the two plates. So if you multiply those two terms together, you can see that the distance between the two plates should cancel, and so the total charge should be whatever the permittivity is times the area of the plate times the magnitude of the electric field between the two plates. Given that as we have current here, the charge is actually changing, it follows that dq dt is equal to the derivative of all of this with respect to time. And since the plate area is constant, and since this is a universal constant, that means that dq dt must be the area of the plate times the permittivity of space times the derivative of the electric field with respect to time. So worth noting, dq dt is actually the same thing as current I, or as conduction current generally. And Moreover, E times A is the flux of the electric field through a surface of area A. Assuming, of course, that the electric field is perpendicular to that surface. So we take the surface to be, for example, like this. So what all this means is that the area times the derivative of the electric field with respect to time is really, since you have a constant surface, the derivative of the electric field flux with respect to time. And so therefore the current should be the permittivity of free space times the derivative of the electric field flux with respect to time. So this conduction current should be equal to the derivative of the flux of the E field produced between the two plates with respect to time. And so now we can generalize Ampere's law, and in this form it is sometimes called the Maxwell-Ampere law. Integral B dot dl is mu naught I plus mu naught epsilon naught d phi dt. So now, instead of just being equal to the permeability of free space times the current, this integral B dot dl around the closed path, the closed Amperian loop, is equal to the permeability of free space times the conduction current that passes through the area bounded by that loop, plus the permeability of free space times this new term that we could call the displacement current, which is permittivity of free space times the derivative of the electric field flux with respect to time. So basically, you could rewrite this equation as mu naught times conduction current plus displacement current. And so now Ampere's law is actually satisfied by this strange case in which you could have a closed path surrounding this wire with one surface passing between the two capacitors and the other not passing between the two. In the case where the surface does not pass between the two, you have a conduction current. In the case where it does pass between the two, you have a change in the electric field flux. So that's basically what Maxwell did. He basically made it so that Ampere's law works even in this odd condition, but then he also noted that this predicts a variety of things, such as electromagnetic waves. Before we get there, there's a second thing of importance, and we've kind of touched on this in previous lectures, which is that Gauss's law can be applied to magnetism. Remember that Gauss's law is the law that says that the flux for the electric field integral E dot dA is equal to the charge enclosed divided by the permittivity of free space. Well, you can also get a Gauss's law for magnetic fields, and what you end up getting is that the flux for a magnetic field through an arbitrary closed surface is always zero. And the implication of that is that there are no magnetic monopoles. So the analog to a magnetic charge has never been found or discovered to exist, and there's never been any evidence that such a thing could exist. Certainly not predicted by classical E&M. So that means that magnets tend to look like dipoles, and therefore if you were to try and put any kind of surface, you'd have some field lines are closed, so any field line that pokes out through the surface will also go back in, and vice versa. So this is Gauss's law in magnetism. So in free space, absent dielectrics, you get Maxwell's equations in integral form. Basically, they are Gauss's law for electric fields, Gauss's law for magnetic fields, the Faraday's law, and then the Maxwell-Ampere law, or Ampere-Maxwell law. And these four equations basically are collectively are the most fundamental of all equations in electromagnetism. You combine these with Lenz's law, which is the force law, F equals QE plus QV cross B, and now you have basically all of classical EM. Those of you who are going to be going on to more advanced physics courses will in fact see these four laws in a different form, namely in differential form. So this is an integral form. In differential form, you basically get some terms that I haven't really defined in the course of these lectures. D and E are related. They both have to do with electric fields. B and H are related. They both have to do with magnetic fields. J, you've seen, is the current density. And rho is basically the charge density, or density of free charges. So I'm not going to derive those from the integral form. That is for a more advanced E&M course to do. But when you get into your junior or senior level electromagnetism course, you will probably see a derivation of these, and most of the course will be unpacking these four equations plus Lenz's law. Maxwell's equations can be summarized sans calculus as a form of a set of predictions. Now, this is for the physics with calculus course that I'm giving this, but this is basically how Maxwell's laws are presented to the non-calculus course as well. Basically, there's a set of four predictions that generally are the summary of Maxwell's equations. Namely, you get electric field lines, and those begin on positive charges, they end on negative charges. Electric field is the force per unit charge on a test charge, and it can be related to the permittivity of free space, which is given by approximately this number, 8.8542 times 10 to the negative 12 farad per meter. And that is called the permittivity of free space. Magnetic field lines, for their part, are always continuous and closed, and so there's no point of origin or termination for them. This is because there are no magnetic monopoles. You can have magnetic dipoles, and they are often produced by moving charges. They are related to the constant of 4 pi times 10 to the negative 7 Tesla meters per amp, and that is called the permeability of free space. And then the changing of a magnetic field in time will induce an EMF, and therefore a changing magnetic field can produce an electric field. And a changing electric field can produce a magnetic field, is the Ampere law, the Maxwell's modification to Ampere's law. And so basically that means that magnetic fields can be produced by one of two things, either a moving charge or a changing electric field. And electric fields in turn are produced by charges in general or changing magnetic fields. Now, the fact that changing magnetic field and changing electric field will produce each other, that is, a changing magnetic field produces an electric field and a changing electric field produces a magnetic field, is a very important point within Maxwell's equations. Note that without Maxwell's modification to Ampere's law, you wouldn't have that symmetry. You'd have a changing magnetic field can induce an electric field, but a changing electric field would not be predicted to produce a magnetic field. Reason why this is so important of an addition is not just because now in this strange realm of the space between two plates in a capacitor, Faraday's law, Ampere's law now works. No, that's not the key point here. The key point and the key prediction between these 2 points is that suddenly you're able to produce electric and magnetic fields without necessarily needing to have charges or moving charges. And the reason why that's so significant is that it now suggests that you can get what's called electromagnetic radiation. So this predicts electromagnetic radiation. Note that if you have a charge which is moving at all, that charge will create a sort of changing magnetic field. It'll produce a changing electric field. That electric field, in turn, can produce a changing magnetic field. And in fact, electromagnetic radiation, as we'll see, originates from accelerating charges. Before we get there, let's talk about Lorentz Force Law again, just for review and just for the sake of completeness. So Maxwell's four equations, or Maxwell's laws, Maxwell's equations, are the core set of equations for classical E&M. You can add to that the electromagnetic force, which is given by the Lorentz Force Law, and that is this equation, which you have seen before. Here's the diagram that basically goes with that. You have a charge Q, it's moving at speed v at some direction theta with respect to the magnetic field. That means that the force from the magnetic field is represented by this blue line, QV cross B. It's perpendicular to B and V. There's also an electric field which produces a force that is in the direction of the electric field. It's a positive charge, QE. And so if you want the total force, you add this force, QV cross B, plus this force, QE, and you get the total force on the particle. So at this point, we now have everything you need to describe any classical electromagnetic interaction in a vacuum. And those equations that I showed before can be modified to describe interactions inside non-vacuum media. Case in point, if we go back up to Maxwell's equations, basically the D and the H terms in these equations are terms that describe what happens inside of media, not just inside a vacuum. Otherwise, it would just be E and B everywhere. This would be E, this would be B. This would in fact also be E. But that's for basically a more advanced course to really get into. So what really validated Maxwell's equations, or the first experiment that really tested Maxwell's equations as such and as predictors of this electromagnetic radiation, is what's called Hertz Experiment. It's done by Heinrich Hertz. And basically what he did is he made a couple of RLC loops. So RLC means resistor, inductor, capacitor. And so really what he had was a AC source. Here's his RLC circuit. There's a transformer. So this AC source goes through the transformer, gets converted into an AC signal over here. Then this one has a loop that has a spark gap. It means there's basically a ball and a ball here and some distance between the two balls. And so charge can build up on the two until sparking happens. And then on the other side of his laboratory, he basically made a second spark gap, which is basically identical to this one, and a tuner, which is essentially identical to all this, but with the ability to tune the resonant frequency. So what's the resonant frequency of this RLC circuit? Well, we discussed that previously in talking about LC circuits and even RLC circuits. The resonance frequency F is 1 over 2 pi square root LC, or if you want it in terms of omega, the angular frequency, you'd have omega naught is 1 over square root LC. So basically you end up building up charge on these two spheres, these two little ends of the wire, or electrical ends of the wire, until you have an electric field between the two of them of about 3 times 10 to the 6 volts per meter. That's the breakdown field strength for air. And once that happens, you get a spark that jumps between the two. And basically, what he observed is that a spark could be induced in this second loop when its frequency is matched to the first loop's frequency. So the tuner frequency is matched to the transmitter frequency by having 1 over root LC equal for this guy as for this guy. Note that there's no AC source attached to this, though. It's just an RLC circuit with no voltage source, no AC source. This one has an AC source in it. So this one's driven, this one is not. And the way that you adjust the resonance frequency is that you can basically change the capacitance of the capacitor or the inductance of the inductor. It's usually easier to change the capacitance of the capacitor, just like what you do in tuning a radio today. You can change the frequency of the capacitor used to tune a radio frequency. And so they basically does the same thing. Since that resonance frequency is 1 over square root LC, you would expect a very large frequency. In fact, his experiment is of order 100 megahertz. Again, that's because both capacitance and inductance tend to be very, very small. Nano or femto even is not unheard of. Pico, micro on a good day, in farads or in henries. So what happened is that when the two frequencies were matched, sparks got induced in the receiver spark gap, which was sort of analogous to what happens when you strike a tuning fork and you place it near a second tuning fork which has not been struck but which is set for the same frequency. You can get some sound out of that second fork. It'll start to vibrate along with the first fork that you've struck. And so the conclusion that he drew was that the induced current, and hence the induced sparks in the receiver, must be caused by electromagnetic waves traveling from transmitter to receiver, just as predicted by Maxwell's equations. So in the case of the pair of tuning forks, it's mechanical waves. In the case of the Hertz experiment, it's electromagnetic waves. So there were several properties that they found for these electromagnetic waves, which actually basically were similar to properties that had been already observed by light. For one thing, they found that you can reflect or refract an electromagnetic wave of any type. Refraction basically means that when you change from one medium to another, the wave bends. And so the direction of propagation actually shifts as you go from one medium to another. Second, he noticed that these waves would undergo diffraction, which basically means that they'll bend around sharp edges. Think of an analogy: if you're standing around the corner from somebody, around the corner of a building, you can still talk to that person and they can still hear you without having to move around the corner so that you're both standing in the same side of the building. So you can stand on the corner and talk, and your friend who is around the corner of the building can carry on a conversation with you just fine, although usually you maybe would walk around so that you can sort of speak face to face. But thanks to diffraction, even though you're speaking here and there's a corner in the way, this guy can actually hear you, and it's not just because sound waves pass through the medium in the building, it's because they are in fact diffracting around this edge. So that is, electromagnetic waves also are able to interfere with each other just like a mechanical wave and just like light. And basically this means that the electromagnetic waves will obey the superposition principle. Given that an electromagnetic wave is basically an oscillation in an electric field and a magnetic field, this should especially not be a surprise after having had these lectures. Recall that if you have an electric field from one source and an electric field from another source, then you can get the total electric field at some point due to those two sources by adding the vector sum of the two individual electric fields, and that is the superposition principle. And finally, the waves share another property with light, which is that they have polarization. It turns out that polarization is thanks to the fact that the electric field and the magnetic field are along separate axes. In fact, they are perpendicular to each other. So the polarization has to do with what is the orientation of the electric field, and therefore what is the orientation of the magnetic field. So light is polarized one way if the electric field is in the XY plane, and it's polarized another way if it's in the YZ plane, for example. So if you want to go into vacuum, then you have no charges and you have no currents. And the result is that you can say Q is 0, I is 0. And so Maxwell's equations in integral form look like this. And notice now that there's even more symmetry, or maybe I should say more obvious symmetry, more evident symmetry than what we had before. Here the flux of the E field is 0 because there are no charges, just as the magnetic field flux is 0. And here the integral of E dot dl is negative d phi dt, and the integral of B dot dl is a couple of constants times d phi E dt. In other words, the integral of the electric field around a closed path is equal to negative of the change in the flux of the magnetic field with respect to time, and the integral of the magnetic field about a closed path is equal to a couple of constants times the rate change of the electric field flux with respect to time. And this last term, this term right here, is the term that Maxwell basically added to Ampere's law, and it's absolutely essential to the production of electromagnetic waves. The electric field and the magnetic field in an electromagnetic wave are related to each other by a pair of basically coupled differential equations. This one says that the rate change of the magnetic field spatially is negative mu naught epsilon naught times the rate change in time of the electric field. And then this one says that the rate change of the electric field spatially, or the variation of the electric field spatially, is the negative of the rate change with time of the magnetic field. And we can obtain these two results from Faraday's law and from the Maxwell-Ampere equation. And this also is the reason why Maxwell's addition to Ampere's law is of such importance in predicting electromagnetic waves. And so basically I can go and get these two equations as a set of derivations. I will not do that right now. I think I'm going to save that towards the end of the video as an actual sort of long example, if you will, to work towards the end. But ultimately, both the electric field and the magnetic field fulfill what's called the one-dimensional wave equation. So this right here is the one-dimensional wave equation. This term right here, this capital psi, represents basically your wave function itself. So the second derivative of the wave function with respect to the spatial parameter is equal to 1 divided by the speed at which this wave is propagating squared times the second derivative of the wave parameter with respect to time. So the wave parameter represents basically, or the wave function I should say, represents the function describing the wave in question. So for an electromagnetic wave, this represents either the electric field or the magnetic field. But this equation actually also describes mechanical waves in one dimension. And in fact, you can get into 3 dimensions by basically taking some derivatives with respect to the other spatial variables. I don't want to get too much into that right now. This wave function is the function that actually is describing the wave itself. So the electric field might be described by some function. The magnetic field might be described by some function. Basically, if you look at a mechanical wave, you'll see that the function is usually something like displacement is equal to the maximum displacement times the cosine of some phase term. So you may recall back when I did the lecture discussing mechanical waves and looking at the picture of a traveling wave, that this right here is the snapshot of for example, a wave on a string. Then each of these points might represent the displacement of a single section of the string from the equilibrium position. The equilibrium position would be 0. And we said that this function is described by y equals a sine of 2 pi over lambda x minus vt, or a sine kw x minus omega t, where lambda is the wavelength. It's basically the distance from one peak to the next, or from one trough to the next, etc. V is the speed of this wave. A is the amplitude, that means the maximum displacement, and omega is the angular frequency. So our usual wave function for a mechanical wave represents some sort of a displacement. You can recall further from that same lecture that I also talked about the other type of wave that you might get, which is a longitudinal wave. Also has the form of a sine wave. There's some additional parameters, and instead of a displacement, it might be the density function, or it might be the pressure of the wave. Although there's also a displacement function that can go with this, in that each particle that initially started at some position is also being displaced from that position in order to create these longitudinal waves. It just happens to be in the same direction as the wave is traveling. So basically this density and that previous equation for y, the displacement, both represent wave functions for mechanical waves. The electromagnetic waves therefore also have a wave function, but in this case it's the electric field and it's the magnetic field. So looking at this picture, you can ascertain, and looking at that set of notes that I showed, looking at the fact that this equation goes for electromagnetic waves, it goes for mechanical waves, etc., you can maybe guess at what the form of the electric field and the magnetic field might be. Basically, both the electric field and the magnetic field will vary sinusoidally. And so both of them have some equation that is of this form. So the electric field is equal to whatever the amplitude of the electric field wave is, times the sine of the wave number times the x, which is position along the wave, minus the frequency, angular frequency, times time. And the magnetic field similarly is the maximum magnetic field, or the amplitude in the magnetic field variation, which would be this, times the sine of the wave number, which again is 2 pi over lambda, times the position, the spatial position at which we're looking at this wave, minus omega t, which again is the angular frequency, 2 pi over the period, times the actual time that has elapsed since this wave first arrived. And looking back at the previous slide, you see that the wave equation goes like d squared of wave function by dx squared is 1 over v squared d squared of wave function dt squared, meaning, in other words, that the second derivative of the wave function with respect to x is equal to 1 over v squared times the second derivative of the wave function with respect to t. And looking down at these two equations, you see that in both of them, where you have a 1 over v squared here, you have a mu naught epsilon naught, permeability times permittivity of free space. So what that basically means is that 1 over v squared is actually equal to mu naught epsilon naught. And therefore, the speed of light can be obtained by taking 1 divided by the square root of mu naught times epsilon naught. You can see that these two are in phase with each other. That means that the phase term, or the argument of the sign, is the same for both. So if you divide the electric field by the magnetic field, the sign terms will cancel, and so you get E over B is equal to E max over B max. And those in turn are actually equal to the speed at which the wave is propagating, which is 1 divided by the square root of the permeability of free space times the permittivity of free space. And so looking at this in that context, saying they're in phase basically means that the two peaks should match up, and in fact they do. Peak for the electric field and peak for the magnetic field arrive at the same time. The troughs arrive at the same time, or the negative peaks. The zeros arrive at the same time, etc. So now we can look at a few short examples. These are going to be 3 short examples from what I've talked about so far in this lecture set. So let's get to them. So we'll begin with this question. Given the maximum electric field strength, what is the maximum magnetic field strength? Well, again, E max over B max is equal to C. And so therefore, B max is equal to E max over C. B max is equal to 555,000 volts per meter divided by C, which has a value of about 3.00 times 10 to the 8 meters per second. And so this gives us the maximum magnetic field strength, which in this case is about 0.00185 Tesla. I want to say something about this before doing the next example. You notice that it seems like you have a really big electric field and a really small magnetic field, and a common mistake is to say that therefore the electric field must be much, much stronger than the magnetic field. And the fact of the matter is that you can't really compare the strength of the electric field and the strength of the magnetic field because they have different units. So yes, the magnitude here for the electric field looks enormous compared especially to the magnitude for the magnetic field, which looks tiny. This is not because the electric field is much, much greater than the magnetic field. It's just because they have different units. A volt per meter cannot be converted into a Tesla. A voltmeter is its own unit. A Tesla is its own unit. They are not equivalent units. Second, if the frequency of the above wave is 140 terahertz, by the way, frequency is given as f in this case, what is the wavelength? This would be lambda. Well, it's a wave, so as you know, the speed of a wave is lambda times f. So that means that the wavelength is going to be v divided by f. So that would be basically 3.00 times 10 to the 8 meters per second divided by 140 terahertz, which is 1.40 times 10 to the 14 hertz. So what is the wavelength for this? Well, it would be basically lambda equals 2.14 times 10 to the minus 6 meters. So 2.14 microns. That means that it is longer wavelength for what this is worth than visible light, which tends to be in the range of about a little under 0.4 microns to a little over 0.7 microns. So this is a bit longer than that. So finally, if the field that we've described above has a maximum electric field strength at t equals 0, what will be the electric and magnetic field strengths after 50 picoseconds? Okay, well, both fields can be given by something like E max times cosine of omega t minus kx, kx minus omega t. I've got these guys backwards, kx minus omega t. And at time t equals 0, you have a maximum. So basically that would mean that t equals 0 implies cosine of kx minus omega t equals 1. For what it's worth, we can pick any arbitrary location in space to represent this. So I'm just going to pick this location because it'll make everything go a little easier. The answer is not going to change though. So now we want E of 50.0 picoseconds. Well, that's going to be E max times cosine of 2 pi f, or negative 2 pi f, times t, which you'll recall maximum E field strength was 555,000 volts per meter. We're multiplying this by the cosine of 2 times pi times the frequency was given as 140 terahertz, so that's 1.40 times 10 to the 14 hertz, and then that's times 50 picoseconds, so that would be 50.0 times 10 to the 12 seconds. So, oops, yes, okay, minus 12 seconds. In any case, if you get rid of this guy and you get rid of this guy, you're left with 100. And so you can see that we're going to have 1.4 times 100 times 50. So collectively, this is 140 times 50. You can see that this is going to be an integer multiple of 2 pi. So that means that the E field is going to be back to its maximum value after these 50 picoseconds, 555,000 volt per meter. And that also means, by implication, that B will be equal to its maximum, which is what we found in part A. That was that 0.00185 Teslas that we found earlier. So at some other time, of course, this may not be true. Maybe we ask for what is it after 1 femtosecond later, or 10 femtoseconds later, or what have you. And then the answer is going to vary. So for t equals 10 femtoseconds, that's 1 times 10 to the minus 14 seconds. You'd have E is equal to 555,000 volts per meter times the cosine of 2 pi times 1.4 by 10 to the 14 times 1 by 10 to the minus 14 So now you're going to have some difference in the electric field. You have in here cosine of 2 pi times 1.4. So whip out your calculator. 1.4 times 2 times pi. And now we need to do basically a cosine of that. And we're at negative 0.809. And so then that times 555,000 gets us this value. So E in this case would be minus 449,004, or if we're keeping significant figures, maybe 000. And similarly, B will be B max times cosine of 2 pi ft. And so this right here will again be the same value as this, and so we would multiply the cosine by 0.00185 Tesla. And so what you'd have is that the magnetic field is negative 0.000149668, etc. So I guess that would probably actually round to 0.00150 Teslas. So that is your electric and magnetic field strength in a traveling wave of electromagnetic radiation. So now I would like to actually do the derivation for these pair of coupled equations. And basically this derivation ends up making use both of Faraday's law and of Ampere's law with Maxwell's addition. And you should notice as I go through this derivation that if you basically leave out Maxwell's addition to Ampere's law, that you cannot in fact get this pair of coupled equations. And the significance of that is that if you have this pair of coupled equations, is basically saying, given that both of these things are varying sinusoidally, then the changes in the magnetic field will produce an electric field, and the changes in the electric field can produce a magnetic field. And if you don't have the Maxwell addition to Ampere's law, then that ends up being not the case. So let's look at how these two coupled equations come about. So the way that I begin this is that I have drawn for myself an electromagnetic wave, and basically the green part represents the electric field variations, which I'm taking to be basically along the y-axis, and then the B is the magnetic field variation, which I take to be along the z-axis, and this blue line is actually also could represent parallel to the x-axis would be sort of the velocity vector for this traveling wave. So it's moving in this direction. And what we're going to do is we're going to use, first of all, Faraday's law, and then later we're going to use the Maxwell-Ampere law. So let's start with Faraday's law, which you'll recall basically says that the integral around a closed loop of the electric field dotted with the basically loop parameter, if you will, the dl, where L is a section of the loop's length, is going to be equal to negative d phi by dt, where d phi is actually d phi b, that is the flux of the magnetic field. So recall that the flux of the magnetic field is basically B dot A, where A is the area enclosed by the loop that we're going to draw, and B is the magnetic field. And in fact, it's actually going to be something like B dot dA with a integral around it, but it's not through a closed surface, only through a surface that is enclosed by our loop. So let's go ahead and pick some part of this wave through which to put a loop. Well, it has to be in the y and x direction, because it's got to be basically in the y direction, because we need to have some side of it that's parallel to the electric field, and then it has to be in the x direction, because we have to have a surface that's enclosed by it, basically this surface, through which the magnetic field can be sort of poking, hence a magnetic field flux. So what are the relevant parameters for this loop? Well, we want this part of the loop to be small, like a dx, and then this part of the loop can be relatively large, like a delta y. So those are basically the two parameters that are going to define this loop. Now, what is the integral E dot dl going to be? Well, because two sides of this are totally parallel to the electric field and two sides are perpendicular to this electric field, and because the electric field is not really varying along one side or another of this, we basically can write that this integral E dot dl is basically like a sum. Basically it will be this electric field dotted with this length minus this electric field dotted with this length, or vice versa. The reason why that is because if we go around this loop, you have that the loop is this way here, it has to be this way here, and then it has to be this way here. We have to go around the loop. So this electric field at this point right here would actually have to be basically, we'll just call it E. And then the electric field right at this point here would be E plus dE, because we've made some small change to the electric field. And basically that means that for this side we have E plus dE dotted with delta y. So E plus dE dotted with delta y, since they're parallel, basically looks like E plus dE times delta y. For this side, for wherever this side is, you have 0 because the electric field is perpendicular to the dl vector, your side that you're dotting the electric field with. And so now we come to this side, and since the side and the E field are in opposite directions, that dot product gives you E times delta y. So I have an E delta y and I have an E delta y. So what I'm left with is dE times delta y. So that's what this integral gets to me. Now let's look at the other part of it, which is the d phi times dt, or d phi by dt, I mean. Well, d phi by dt is basically the flux, or the derivative, excuse me, of this flux of this magnetic field with respect to this area. So basically we can write that as d by dt of, and since this is the flux B dot A, we have B dot A, and so that actually becomes d by dt of B times, for our area, we actually can, if we approximate it as being this rectangle, your area is delta y times dx. So we have B times delta y times dx. And delta y and dx are not variant with time, only this magnetic field is. So what that basically means is that d phi B by dt must be given by delta y times dx times dB by dt. So this one right here was integral E dot dl, and that gave us this. This right here is what we got from the derivative of the flux with respect to time. So now we basically put them together via Faraday's law. And so what you end up with is dE delta y is equal to delta y times dx dB by dt, with a negative over here because this was actually equal to negative of this derivative of flux. Since we have a delta y on both sides, we can go ahead and divide both sides by a delta y and hence cancel that out. And then while we're at it, we should go ahead and divide both sides by a dx. And so what we end up with is dE by dx is equal to dB by dt, negative dB by dt. And you may be wondering, because in the equation it's a partial derivative, this one right here is not a partial derivative, it's an actual derivative, if you will, a plain old ordinary derivative. So why the notation change? Well, the answer is because both E and B are functions of x and t. We want to be sure that we're just taking the derivative of E with respect to x, and we want to be sure that we're just taking the derivative of B with respect to t. And so that's where the partial derivative comes in. So that is the first of the two equations. Actually, that's the second of the two equations that I showed on that set of notes. It is the one that comes out of the Faraday's law. So now let's look at the one that's going to come out of the Maxwell-Ampere equation. So I'm going to go ahead and start back over again with my wave drawing. Nothing here has actually changed compared to the previous drawing that I have. I've just kind of cleared my workspace around it. And what we want to do here is use the Maxwell equation. the Maxwell-Ampere equation. So first of all, what would happen if we just used Ampere's equation as such? Well, Ampere's equation as such says that the integral around a closed loop of B dot dl is equal to mu naught times I enclosed. So around the closed loop here that we have, we need to pick a closed loop that is in the direction of our magnetic field. So our closed loop basically ends up being something like this. So here's our closed loop, and there's not really any enclosed current, so that's kind of anticlimactic. Basically you end up with just zero, and that's what happens if you stop with only Ampere's equation. Okay, well, what if we don't have just Ampere's equation? Well, the Maxwell addition to Ampere's equation says that we need to add, in addition to the conduction current, we need to have our displacement current, mu naught epsilon naught times d phi for E over dt. d phi E by dt is the derivative of the E field flux with respect to time. So again, our electric field flux basically looks like E times A, or E dot A. So now again, let's do this sort of piecemeal. First we'll take the integral of B dot dl. Again, this part right here, the conduction current is zero if we're in free space. So B dot dl is going to be the integral of this magnetic field as we move around this basically closed loop. So the closed loop needs to be like so. And this closed loop that we're going around, you have basically, again, a dx. So this is dx. And you have, again, a delta something, but in this case it's along the z-axis. So this right here would represent a delta z. And so what are the magnetic fields at each of these points? Well, the magnetic field right here will represent as B. The magnetic field here is basically B plus dB. Okay, so now we are again doing an integral around this loop. Again, there's no field that's parallel or has any component parallel to this side or this side. And so we can basically do the magnetic field for this side, which is, as I've drawn this loop, basically it will go negative of B plus dB times delta z. And then for this loop, the field is in the same direction as the loop, and so we have plus B, and again this is a delta z, so times delta z. Alright, so basically what that means is that we're going to have a negative B delta z and a plus B delta z. So those terms go away, and we basically end up with that for this side, B dot dl, the integral of that around the closed loop, is negative dB times delta z. So now we need to do this other side. So mu naught times epsilon naught times d phi E by dt. Let's actually just ditch the mu naught and epsilon naught part because we can plug it in later. So dE by dt is going to be equal to the derivative with respect to time of E dot A. Well, that is d by dt of the electric field times the area. In this case, the area is like this, and so the electric field is poking through it this way. The area is dx times delta z. So this becomes E times delta Z times dx. And again, these two things are invariant with respect to time. When you take the derivative with respect to time to delta Z or to dx, you don't get anything, or you get zero, I should say. So you're left with dE by dt. So this term here that's on the right-hand side ends up looking like this. The derivative of the flux of the electric field with respect to time is equal to delta Z times dx times dE by dt. Alright, so now what we do is we actually use the Ampere Maxwell equation and set these guys equal to each other. So this right here and this right here must be equal, as long as we remember our constant mu naught epsilon naught. So we have negative dB delta Z is equal to mu naught epsilon naught times delta Z times dx times dE by dt. And again, there's delta Z's on both sides, so those delta Z's sort of cancel with each other, and we can divide by a dx for both sides, and that gets rid of the dx over here. And so what we're left with is, and maybe we can redistribute the minus sign, we're left with dB by dx is equal to negative mu naught epsilon naught dE by dt. And again, B and E are both functions of x and of t. So this really should be written as dB by dx is equal to negative mu naught epsilon naught times dE by dt. And the reason why, again, why we're putting a partial derivative is to remind ourselves that this right here is a derivative with respect to x of b while time is held constant. And this is a derivative of e with respect to t while x is held constant. So that's what these partial derivatives do. When they're written in this form, it says that t need not be held constant for this, and that x need not be held constant for this. And that's not something that we necessarily actually want. Okay, so we have now derived these two equations on this set of notes. Again, we did that using the Faraday's law and the Maxwell-Ampere's law. From these two equations, we can actually get both of these. And the process basically looks similar in both cases. So I'll actually show how you do that quickly here. So we start with our pair of equations that we just derived. And what we do is, for equation 1, we want to take the derivative with respect to x for both sides. And so what that ends up looking like is that we have dE dx, we take another d by dx, and so that's d squared e by dx squared. And then on the other side, we're taking a derivative with respect to x, so we can actually write that as d squared b by dx dt. Okay, so that's basically our modification to equation 1. For equation number 2, what we do is we take the derivative with respect to time for both sides. And so what that ends up giving us is dB by dx and d by dt. So we have d b dx, so that becomes a d squared b, and the order that you take derivatives in doesn't matter. It doesn't matter whether you take the derivative with respect to x, then with respect to t, or the other way around. So we can write that like this. And then on the other side, we take the derivative of this guy with respect to t. And again, these two are fundamental constants, so they stay outside the derivative. And so you end up with d squared e by dt squared. Okay, so now we notice that this term in this equation and this term in this equation are the same term, other than that there's a minus sign here and no minus sign here. So if we basically get rid of a minus sign like this, then we can set this and this equal to each other, because basically the left-hand side of this and the right-hand side of this are matched with a common term on the opposite sides. And so collectively, what that means is if we want to get rid of the minus sign again, by doing something like this, we would have d squared e by dx squared is equal to mu naught epsilon naught d squared e by dt squared. And so there you have it. We just derived this equation for the electric field. What about for the magnetic field? Well, if you want to do for the magnetic field, then instead of taking d by dx for both sides, we do d by dt for one, and we do d by dx for 2. And the result ends up being that instead of ending up with all e's, you get that number 1 gives d squared e by dx dt is equal to negative of d squared b by dt squared. And 2 then gives basically d squared b by dx squared is equal to negative mu naught epsilon naught d squared e by dx, should be a dx dt, so by dx dt. Okay, so we need to somehow get rid of this mu naught epsilon naught term that's on this side. So we're just going to go ahead and divide both sides by negative mu naught epsilon naught. So minus 1 over mu naught epsilon naught. And so what you end up doing with that is that now we have this term and this term which are the same, and so that means that this term and this term must also be the same. So by setting those equal to each other, what you end up with is minus 1 over mu naught epsilon naught d squared b by dx squared is equal to minus d squared b over dt squared. And so we'll just end up moving this guy over to here by multiplying both sides by a negative mu naught epsilon naught. And so what you end up with is d squared b by dx squared is equal to mu naught epsilon naught d squared b by dt squared. And so now the two expressions that are in boxes match with the two expressions that are in boxes at the bottom of this discussion of plane electromagnetic waves. We basically derived these two equations, and you can see that these two equations fit with the one-dimensional wave equation. And so we basically have now shown that both the electric field and the magnetic field should behave as waves. Notice that in all of this, I never once made reference to either B or E being a sine wave. In fact, I never had to assume a sine wave solution for E or B during all these derivations. Instead, I started with Maxwell's equations, specifically with the latter two of Maxwell's equations, and went from there. And I never had to posit any particular form for E and B. So the fact that they then vary sinusoidally comes from the fact that we have to have something that actually is a solution to this wave equation. And this wave equation should be valid for any linear wave that is not damped or not growing, at the very least, I should say. And so basically that means that both E and B will vary like a sine wave. And so that's where that came from. So therefore, Maxwell's equations do in fact predict electromagnetic radiation, and they do so only in the form as modified by Maxwell. Again, if you don't have Maxwell's modification to Ampere's law, you don't get the set of equations, this term, dE by dx equals dB by dt, and without this equation, you cannot get to this equation. So in fact, without this one, you can't get to either one of these equations. That means you can't get to either one of these waves. And so that is the importance of Maxwell's extra term that he's added to Ampere's law. That's the big relevance to it. He basically started with the question of what happens inside of a capacitor, which is an interesting, though seemingly minor thing, sort of minor application. He played with that, he came up with a solution to it, and then his solution made a prediction, namely electromagnetic radiation, which then became one of the most actually important predictions in all of physics. Maxwell's equations actually are some of the most fundamental equations in all of physics. Maxwell equations basically might be ranked up there with, for example, Newton's laws of motion as far as their importance goes. And so basically there you have it. So that's all that I was going to do in today's part of this lecture set. I've basically introduced to you Maxwell's equations, every one of which you've basically seen before, save for the Maxwell-Ampere's law. And then I've introduced a few wave equations that go with electromagnetic radiation. The most important of those for our purposes probably is that the ratio of the electric field to the magnetic field strength at any point in time is the speed of light, and that they are locked in phase with each other. So that means that the maximum electric field divided by the maximum magnetic field also gives the speed of light, which is also given by 1 divided by the square root of the product of the permittivity and permeability of free space. So that's it for today, and that's it for this part of the lecture. So thank you for watching.